This was what we did in the last class. So this is the rational horizon diagram and the PZX triangle. So you remember everything? Okay, all right. So let's close this down and let's move on to circumpolar bodies. Give me a minute, I'll post the circumpolar bodies. In this presentation, we are going to learn polar is making circles around the pole. Now, fundamentally speaking, all the celestial bodies, they move in circles around. All the celestial bodies move on their declination circles, and all these declination circles are centered at the pole only. But as far as the circumpolar term is concerned, we call those bodies as circumpolar whose circular motion is visible to us. The complete circular motion around the pole is visible to us. In other words, a body is said to be circumpolar if the body is always above the rational horizon of the observer. That is, the body should not set. During the full day, the body should not set. These type of bodies are called as circumpolar bodies. They remain above the horizon of the observer, and you are able to visualize or you are able to see them at any time of the day for full 24 hours. Now let's try to understand when does a body become circumpolar, or what are the conditions which lead to a body becoming circumpolar. This can be easily understood from a rational horizon diagram. Now let's assume that our observer is in northerly latitude in the north hemisphere. You can assume latitude of the NESW points on the rational horizon. Then we mark the celestial meridian of the observer. We mark the prime vertical circle. Exactly at the center of this diagram is the zenith of the observer, represented by Z. Now, since the observer is in the north hemisphere, the latitude is north, equinoctial will be passing south of the observer. So from point Z, if we go down south equal to our latitude, now that gives us the point from where the equinoctial will be passing. It is represented as point Q in the rational horizon diagram. We are aware that equinoctial always passes from west and east points. So now we know that the equinoctial will pass from W, Q, and E. And we can now show the equinoctial in our diagram. We have the equinoctial here. Now, once the equinoctial is there in the diagram, we can also show the pole. In this case, the observer is in north hemisphere, so the north celestial pole will be the elevated pole or the visible pole, and it will be 90° away from the equinoctial. So 90° away or 90° north of the Q point, this is where the pole would lie. So let's mark this point as P, representing the north celestial pole. Now in this diagram, let's assume some celestial bodies of different declinations and let us see whether they become circumpolar for this particular observer or not. Let us first assume a body with a declination opposite to the latitude. The latitude in this case is north, so let's assume a body having a southerly declination. Now in this diagram, we are aware that this N point is on the horizon. The P point represents the pole, and this N to P, what is highlighted by this yellow line, is called as the elevation of the pole or the altitude of the pole. And this is always equal to the latitude of the observer. We can easily understand it from the diagram. Now, the N point is 90 degree away from the Z point, from the zenith, because every point on the rational horizon is 90 degree away from the zenith of the observer. Similarly, the P point, which represents the pole, is 90 degree away from Q point, which is the equinoctial. So P to Q is 90 degrees, that is pole to equinoctial. N to Z is 90 degrees, that is rational horizon to zenith. So therefore, what is the arc ZQ? It will be exactly the same as arc NP. ZQ was the latitude of the observer, so NP, which is the altitude of the pole or elevation of the pole, will also be equal to the latitude of the observer. So let's now assume some celestial body. As I told you, first let's assume a body having a southerly declination. So we have a star here. You can see it is south of the equinoctial, having a southerly declination. Let's try to show the path of this star, the path on which this moves, that is the declination circle of this particular star. All the declination circles are parallel to the equinoctial. So the declination circle of this particular star parallel to the equinoctial would appear something like this. The declination circle shows us the path on which the body moves. Now this body is going to rise at this particular point on the horizon. You can follow the laser pointer on the screen. This is the point where the body is going to rise on the eastern horizon. After rising, it will move on its declination circle. It will cross the meridian of the observer at this particular point and then cross over to the western side, and eventually it will go and set at this particular point on the western horizon. And we can see here that this body is certainly not circumpolar, because at this particular point it is going to go below the horizon of the observer. Now you could have picked up a body of any southerly declination lying between Q and S points, and you will see that all those bodies' declination circle will hit the western horizon at some point, making that body go below the horizon. So any body with a declination opposite to the latitude will not be a circumpolar body. So this is one thing which we have seen now. Now let's assume a second celestial body with its declination of the same name as latitude of the observer and see whether it becomes circumpolar or not. So you can see in the diagram, this is the rising point of the body. A body moves in this particular direction represented by the arrow and then eventually sets at this particular point. Now let's assume a second body here. Now this star is north of the equinoctial, and the declination of the star is of the same name as the latitude of the observer. Let's try to show the declination circle of this particular star. The declination circle will pass through the body and it will be parallel to the equinoctial. So this is how the declination circle is going to appear. On this declination circle, the body will be moving in this particular direction represented by the arrow. The body will be rising at this particular point, moving in this particular direction, crossing the meridian here, and at this particular point the body is going to set. So we saw that even this particular body is not circumpolar. So it is not necessary that with lat and dec of the same name a body should certainly be circumpolar. Let's try to increase the declination a little bit now. Let's assume a third body, this particular star now. This is also having a northerly declination, but the declination is more than what we had in the previous case. Let's try to draw the declination circle of this particular star. Now declination circle will pass from the body and it will be parallel to the equinoctial. Now in this case, the declination circle is going to be like this. All the declination circles are centered at the pole. So centered at the pole, polar distance equal to px, pole and the body. If you draw a circle, that gives you the declination circle of this particular star. Now the arrows show the direction in which the star will be moving on this particular circle. Now we can clearly see that the entire declination circle of this particular star is above the horizon of the observer. It touches the horizon at the north point but never goes below the horizon. So these bodies which remain above the horizon of the observer for full 24 hours and never set are circumpolar bodies. So one thing we have seen from this diagram that it is certainly not possible to have a body circumpolar with lat and dec for opposite names. So one condition which we can pick up from this rational horizon diagram is that for a body to be circumpolar, the first condition is the latitude and declination. Latitude of the observer and declination of the body should be of the same names. Any doubts coming up to here, beta?
Sir, if latitude and declination is same value on same hemisphere.
You mean to say lat and dec are of the same name and the value is also exactly same?
Yes, sir.
Beta, it is not related to body getting circumpolar. It may be circumpolar, it may not be circumpolar in that case. Only thing is if lat and dec are exactly same in name as well as magnitude, then the body will be passing exactly on top of the zenith. That is the thing which you can correlate, but it has got no relation with circumpolar criteria.
Okay, sir.
Okay. In the next slide, we will see what is the second condition making a body circumpolar.
Okay, sir.
Okay. Now in this diagram, I have also shown the polar distance of the body, P to X. This represents the polar distance of this circumpolar star, and it is always equal to 90 minus declination. So polar distance in this case, which is 90 minus declination, is shown in the diagram. Now we can clearly see in this particular diagram that for a particular body to be circumpolar, the polar distance of the body, which represents the radius of the declination circle, should always be less than or equal to np. If the polar distance is more than np, then you can clearly see from the diagram that the declination circle will go beyond the horizon of the observer. It will go below the horizon of the observer, making the body not a circumpolar body. If it has to be circumpolar, the radius of this circle, that is px, should be equal to or less than np. If the radius is equal to NP, you will have exactly this particular condition. The circle will be touching the horizon at point N. And if the radius is less than NP, then the entire circle will be within the rational horizon of the observer. So we understand from this diagram now that for a body to be circumpolar, this condition should be met. That is, the polar distance of the body should be equal to or less than the elevation of or NP. Now, NP or elevation of the pole is equal to the latitude of the observer. So we now come to this relationship that Px, which is the polar distance, should be less than or equal to Np, which is the latitude. Now polar distance is equal to 90 minus declination. So this converts the relationship into 90 minus declination should be less than or equal to the latitude of the observer. Now if I take declination to the other side, to the right hand side, the relationship becomes latitude plus declination should be greater than or equal to 90 degrees. So this is the second condition which needs to be fulfilled for a body to become circumpolar. The first condition which we saw in the previous slide was that the latitude and declination should be of the same names. The condition which we saw in this particular diagram is latitude plus declination should be greater than or equal to 90. So these are the two conditions which needs to be met for a body to become circumpolar. Latitude and declination same names, and latitude plus declination greater than or equal to 90 degrees. So remember these two conditions for a body to become circumpolar. Any doubts, beta?
Sir, in this diagram, initially you said when the latitude and declination are different name. So वहाँ का एक statement I just could not understood, sir. If the things latitude and declination are different, then its circle will be passing through the other side of the pole, sir.
Other side of the pole.
So when these are different in the names, sir.
Okay, I will explain you once again. I'll explain you once again what I explained in the last slide. See beta,
Okay.
if the declination
Yes,
of the body is opposite to the latitude of the observer, like the latitude in this case is north, and you consider the body with south declination. If we consider this body with south declination, you see the declination circle of the body will go below the rational horizon. It is going to set at this particular point where it is mentioned as set.
Okay,
so the circle is going to go below the horizon, so the body will go below the horizon, making it not circumpolar.
Okay, sir.
Okay, beta?
Yes, sir. Thank you, sir.
Okay. Now what you are saying, other side of the pole, that happens with circumpolar bodies. I will show you what it is called.
Okay, sir. Thank you.
Okay. Now we have seen that when a celestial body becomes circumpolar, it remains above the horizon of the observer for full 24 hours. Now, if the same concept is applied to the sun, that means for a particular observer, if the sun becomes circumpolar, it will mean that the sun will remain above the horizon of the observer for full 24 hours of the day. This will result into what we call as a continuous day or a 24 hours day. In some of the questions, this concept of continuous day or a 24-hour day is used. So in these type of questions, we should be aware that if the sun becomes circumpolar for an observer, he will have 24 hours daytime and no night. This happens close to the poles in higher latitudes above about 66.5 degrees north and south. In the polar regions, you have 6 monthly days and 6 monthly nights. Whenever the sun's declination matches with the declination of a particular pole, it will always remain above the horizon for that observer, leading to 24 hours day. So thus, if the sun fulfills the circumpolar criteria, there will be a 24 hours day and there will be no night for that particular observer. So in case the conditions for continuous day are asked to us in the question, they will be same as the conditions for circumpolar bodies. That is, the latitude of the observer and the declination of the sun should be of the same names, and the latitude of the observer plus the declination of the sun should be greater than or equal to 90 degrees for the sun to be circumpolar, resulting in a 24 hours day or a continuous day and no night at that particular latitude. Any doubts, beta? Very good. Now, in some of the questions, instead of asking the conditions for a continuous day or 24 hours day, they ask us the conditions for a continuous night or a 24 hours night. It basically means that the sun should remain below the horizon of the observer for the full 24 hours, and in that case, the observer will have 24 hours night and there will be no day. There will be no sunrise, there will be no sunset. The sun is going to remain below the horizon of that particular observer for full 24 hours. Now, this condition is possible when the following conditions are fulfilled. Number one, the latitude and declination should be of the opposite names in this case. For sun to remain below the horizon or for a continuous night or 24 hours night, the latitude and declination have to be of the opposite names. It is only possible when the lat and dec are of the opposite names. And the second condition is that latitude plus declination of the sun should be greater than 90 degrees. So these are very similar to the circumpolar conditions, only difference being in circumpolar the latitude and declination should be of the same name, and in a 24 hours night scenario or continuous night scenario, the latitude and declination should be of the opposite names. We can understand it very easily from the rational horizon diagram. You can see this rational horizon diagram. We have an observer in the northern hemisphere. We can see the pole. We can see the equinoctial as WQE. Now, in this diagram, we are aware that the portion or the arc ZQ represents the latitude of the observer. Q is the equinoctial, Z is the zenith. So ZQ represents the latitude of the observer. Now our first condition says that the declination should be of opposite name to the latitude. So in this case, if the latitude is north, the declination should be south. South declination means that the sun would be below this point Q. So the sun would be southwards of point Q which represents the equinoctial. The sun will be southwards of the equinoctial. Now, if the sun is between point Q and point S, it has southerly declination, but it will still be coming above our horizon. If the sun passes our meridian between Q to S, it will still be coming above our horizon. There will be a sunrise and there will be a day for some parts of the 24 hours. But if the declination circle of the sun goes beyond point S or further south of point S, then in that case, the entire declination circle of the sun will remain outside our rational horizon and the sun will never come above the horizon. So let me show you in the diagram. If the declination of the sun is such that it has gone beyond point S or southwards of point S in our diagram, you can see the declination represented in maroon, and the declination is such that the sun has gone beyond point S. In this case, the declination circle of the sun, you can see this dotted line showing the declination circle of the sun. The entire declination circle of the sun will remain below the observer's horizon, making it a 24 hours night. There will be no sunrise, the sun is not going to come above the horizon of the observer, and there will be no daylight. Now, we are aware that from the Z point to the S point, Z is the zenith, S is the south point on our rational horizon, the total arc length is 90 degrees. From the zenith to the horizon, the arc length is 90 degrees. And we know ZQ is the latitude. Now, this is the declination Q to S. So if latitude plus declination is greater than 90, it immediately tells us that the declination circle will pass beyond our rational horizon, or the sun is going to remain below our rational horizon. So that's why the condition latitude plus declination of sun should be greater than 90 degrees for the sun to remain below the horizon for 24 hours, resulting in a 24 hours night or a continuous night. Whenever the sun has a northerly declination, in that scenario, the south pole has a continuous night or a 24 hours night, because lat and dec are of opposite names and the latitude plus declination is greater than 90. The same thing happens when the sun is having a southerly declination. There is a continuous night or 24 hours night on the north pole. Any doubts, beta? Very good.
Sir, it's not equal to lat plus declination of sun is not equal to 90 because when it is equal to 90, it will be at point S.
That's correct, beta. If it is equal to 90, the sun will be just touching the horizon at point S and you will be able to see it for a very short period of time. So that's why equal to is not included.
Right, sir.
Okay.
Sir,
Go ahead,
this
beta.
is vice versa condition of circumpolar body, correct, sir? Or
Say
almost.
again.
This is just opposite to the circumpolar condition.
Yes, that's right, beta. That's exactly right. In circumpolar, lat and dec are of the same name. In this, lat and dec are of the opposite name. That is the only difference. So it's basically, you can say, opposite to circumpolar.
So this is applicable only for the sun or any other body, sir, also?
No,
same?
for all bodies, beta. If you
Okay.
apply it to some other body, then
Okay.
it will not be day and night, because day and night are associated with the sun only. But
Okay.
if you apply it to any other body, then the other body will remain below your horizon for full 24 hours. It will never come above.
Okay, okay, sir. Thank you, sir.
Okay. Good. Now, going a little more deeper into the circumpolar bodies, we had this particular star. and the polar distance is less than or equal to NP in this case, and you can see the entire declination circle of the star is within the rational horizon of the observer. So this is a circumpolar star. Now the direction of this the motion of the star is represented by these two arrows. Now in this particular diagram we can see that the star comes north of the observer at two instances. At point A here, it will be north of the observer. The bearing of the star would be 0, 0, 0. And again, when it reaches or crosses the meridian at point B, it will be again north of the observer with a bearing 0, 0, 0. Now this is only possible in case of a circumpolar body. For a normal body which is not circumpolar, it will come north or south of you, or in other words you can say it will come on your meridian only once in a day. But a circumpolar body will be north or south of you twice in a day. Roughly after an interval of 12 hours, it will be south or north of the observer 2 times in a day. Now both of these instances are called as meridian passages. One of them is the meridian passage on the observer meridian. If you look carefully in the diagram, P is the pole and P, Z, Q, S is the observer's meridian, and you can see that at point B the body crosses the meridian of the observer. Now at the second instant, that is at point A, it is crossing the inferior meridian of the observer, or the opposite meridian of the observer. You see, when you go on other side of the pole, this represents your inferior meridian, reciprocal meridian. So at point A, the body crosses the inferior meridian of the observer. At point B, it crosses the meridian or the observer's meridian. Now point A is known as meridian passage on the inferior meridian. You can call it the meridian passage of the body on the inferior meridian, or you can also call it meridian passage below the pole. Now why do we call it meridian passage below the pole? That also can be seen easily from this diagram. We know N to P is the elevation of the pole or the altitude of the pole. So N to P represents the elevation or altitude of the pole. N to A represents the elevation or altitude of the body at the time of meridian passage on the inferior meridian. And we can clearly see that the altitude of the body is lesser than the altitude of the pole. That is why at this particular instant, that is at point A, the meridian passage of the body occurs below the pole. Now this is, for this particular reason, this is also called as lower meridian passage or lower Marpas. At the same time, the point B which you see is known as the meridian passage on the observer's meridian. Point B represents the meridian passage on the observer's meridian. It is also called as meridian passage above the pole, because you can see at this point the altitude of the body is represented by NB, November Bravo. The altitude of the pole is NP, November Papa, and the altitude of the pole is less than the altitude of the body. The body is at a higher altitude at point P. So that is why it is called as meridian passage above the pole. And it is also known as upper Marpas or upper meridian passage, because at point B the body is above the pole. It is at a upper location than the pole. So upper Marpas and the lower Marpas. Upper Marpas or meridian passage above the pole is on the observer's meridian. Lower Marpas or meridian passage below the pole is on the observer's inferior meridian. Now, if you remember, when you look for the meridian passage time of the moon in the almanac, there are two times which are given, one under upper and other under lower. This upper and lower basically means the meridian passage of the moon on the observer's meridian, that is for upper, and for lower, it is the meridian passage of the moon on the observer's inferior meridian. Any doubts, beta? Very good, beta. Let's now practice a numerical question based on the concept of circumpolar bodies. We have the basic understanding of the circumpolar bodies now. So let's go into this question. The question says, to a stationary observer, an unknown star bore 000 true with a true altitude of 78 degrees 12 minutes. After about 12 hours, the same star bore 180 true with a true altitude of 18 degrees 54 minutes. We have to calculate the observer's latitude and the star's declination. So a very straightforward and simple looking question. You observe here in this question that the star is bearing 000 at a particular time, and after about 12 hours it is again bearing 180. So at one time it was north, at other time it was south. So this is only possible in case of a circumpolar body. Otherwise, for bodies which are not circumpolar, they come north or south of the observer only once in 24 hours. Anyway, let's now try to see how do we solve these type of questions. Now, all circumpolar questions can be solved using a single approach. If you have that approach clear in your mind, you will be able to attempt any question based on circumpolar bodies. Not only circumpolar bodies, later on we will also see the questions based on rational horizon diagram, and the same approach is applicable to those questions also. So what is this approach with which we can solve these questions? The approach is that in all these questions you make a rational horizon diagram. Make a rational horizon diagram, and whatever information is given to you in the question, a true altitude or a bearing, whatever is given to you, try to put all that information in that rational horizon diagram itself. Now, when you put all the information, what was given in the question, in the rational horizon diagram, the diagram itself will give you a lead into solving the question. For circumpolar bodies, you will not even need to use a formula. No formula is required. Only by adding or subtracting, you will be able to find your answer. But in other rational horizon question, once you put all the information in the diagram, you will be able to solve it by a spherical trigonometry formula. A PZX triangle is formed, and you are able to solve it using either the cosine formula or the Napier's rule. So let us apply this approach in this particular question and see how it works. Let's draw the rational horizon of the observer. Let's mark off the NESW points. And at the center of this diagram, we have the zenith represented by Z exactly in the center of this diagram. So let's try to put the information now what is given to us. The star is bearing 000 with a true altitude of 78 degrees 12 minutes. Now in this diagram, the 000 bearing or north bearing is represented by line NZ. Line NZ represents the north bearing or 000 bearing. So the star has to be somewhere on this line. Now point N being on the horizon is at 0 degree altitude. Point Z being the zenith of the observer is at 90 degree altitude. The altitude which we require is 7812. So from the horizon going 7812, somewhere here is going to be our star. So let's mark off this altitude in green. You can see the green color line on the plot now representing altitude of 7812. And this is where we have the star. So unknown star is bearing 000 and it is at a true altitude of 7812. Any doubts up to here, beta?
No, sir.
Very good. Now after about 12 hours, the same star bore 180 true. Now 180 bearing is represented by line ZS, and on this line we have to mark a true altitude of 1854. S is the horizon, 0 degree altitude. Z is the zenith, 90 degree altitude. So from the horizon we move 18 degrees 54 minutes up. From the horizon we move 18 degrees 54 minutes up, and this is where our star is. So let's mark off the star here. You can name this location as Y. The initial location where the star was bearing north is named as X, and at southerly bearing the star is named as Y. So you have all the information what was given in the question in the diagram now. Now these X and Y indicate the location of the same star. Now if the star is at X location at one point of time, and after about 12 hours it is at Y location, that means the declination circle of the star has to be such that it passes from both X and Y. The declination circle should be such that it passes from both these points X and Y. Now there is only one possibility of how the declination circle is going to be, and that possibility is the declination circle passing from both the locations in this way. There is no other circle which you can draw in this diagram so that point X and point Y lie on that same circle. So this is the only possibility of the declination circle of the star. So you see, once we have position X and Y known to us, we can easily make the declination circle of the star. So this is the approach. Now from the declination circle, now we can also identify the pole. We are aware that all the declination circles are centered at the pole. Now we have the declination circle of this particular star. So that tells us that at the center of this circle will be the pole. So let us draw the pole. It will be at the center of this particular circle. The center is going to be here. So let's mark the center of this circle. This is where the center is, and let's mark this as point P. So we have the pole in our diagram now as the center of the circle, and we can also mark off the direction in which the star is moving in this circle. These green arrows, they represent the direction in which the star will be moving. All the celestial bodies, they rise on the eastern horizon. They go up to the meridian of the observer and they set on the western horizon. So this is the direction in which the bodies appear to move. So we have the center at the pole, center of the declination circle. Now moving further.
Sir, my first condition we discussed that latitude and declination should be of same name, right?
That's right, beta.
But here, I think it is not same hemisphere. Is it correct, sir?
Beta, latitude is not found yet. We will be finding the latitude. The declination is certainly south. The latitude is not found yet. We'll be finding it now.
Okay, sir. Okay, sir. Thank you.
Okay. To see, the distance n to x is 78 degree 12 minutes and the distance s to y is 1854 minutes. Now we know that from s to z is 90 degrees and from z to n is also 90 degrees. So total distance from n to s is 180. The diameter of this diagram, the rational horizon diagram, is 180. If n to s is 180, we know nx 7812 and we know sy 1854, then in that case we can easily find out this particular distance, that is from x to y. It will be 180 minus 1854 minus 7812. So xy in this case comes to 82 degrees and 54 minutes. So xy is 82 degrees and 54 minutes. Now this xy is the diameter of the declination circle. If you divide it by 2, you will get the radius of this declination circle. So 8254 divided by 2 gives you 4127. So this 4127 is the radius of this circle, which is equal to px or py. So polar distance of the star p to x is the radius of this declination circle. Once the pole is there in the diagram, we can also mark off the equinoctial. The point Q of the equinoctial is 90 degrees away from the pole. So we have the pole here. 90 degree away from the pole is this point Q on the equinoctial. And we know equinoctial always passes from east and west points. So joining W, Q and E, we can mark off the equinoctial in our diagram. Now we know the polar distance px, we have calculated it as half the diameter, it is 4127. From this, we can now find out the declination of the star, which is basically how far away from the equinoctial this star is, that is q to x. And this declination is equal to 90 minus polar distance. You can see p to q is 90. P to x is 4127, that is the polar distance. So Q to x will be 90 minus 4127, that is 48 degree 33 minutes. So Qx, which is the declination of the star, is equal to 48 33 minutes. And we can see in the diagram that the star is south of the equinoctial, so the declination is south. 4833 south. So this was one of the items which was required. The star's declination has been obtained as 4833 south. Any doubts, beta?
Sir, I have a query regarding this diagram, sir. One more.
Go ahead, beta.
Sir, I also make a diagram, but my question is, sir, you are taken this one 18 degree 54 inch means second star altitude. That is you taken south pole. First you are measuring from north and second is south pole, sir. The region behind that, sir.
Okay, beta.
And I have
Look at
making a diagram, but I've taken only north pole, and the rest other thing will be. I
okay.
start same,
No.
but later
Okay,
on my
okay.
direction will be wrong, sir. So that just I want to try to understand what mistake I have done, sir.
Okay, beta. Look at the question, beta. The first line says us The unknown star bore 000 with true altitude 7812. So this 7812 altitude should be from the north point of our horizon. That is what is 000.
Okay, sir.
And in the second line it says the same star bore 180 with the altitude of 1854. Now 180 represents the south point. So 1854 has to be from the south point of the observer, beta.
Okay, sir.
Sir, also the selecting the pole, how do we decide, sir? It should be on the south or north in this condition?
Okay, beta. Okay. Whenever in this diagram you have the pole southwards of the zenith between Z and S, it will always be the south pole. Okay, it will always be the south pole. It cannot be the north pole. And whenever you get a pole between Z to N, November to Zulu, anywhere in between you get the pole, it will always be the north pole and not the south pole.
I didn't get, sir. Can you tell again, please?
So, sir, my
Hold on, beta.
understanding
Let's
was
first clarify. Let's hold on. So you did not get which pole is this, beta? The P
Yes.
which we have shown, whether it is south pole or north pole. Okay.
No, sir. Why we have selected the south pole, that I am having doubt. Why
Okay,
we have
beta. You were able to make the circle, the declination circle you were able to make.
Yes, sir.
Now tell me, what is at the center of all the declination circles?
Pole, sir.
So at the center of this circle, we have to have the pole. That's why the P point.
Okay, sir.
Okay.
Okay, that is why we have selected south pole.
Exactly, beta. If you can get a declination circle of the body in your diagram, the center will always be the pole. And now
Yes,
the
sir.
second doubt arises is it the north pole or is it the south pole? That is not known.
Yes, sir.
Whenever the pole is southwards of Z, it is always the south pole, beta. North pole cannot come southwards of Z.
Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Okay, beta. Now go ahead with the next doubt.
sir. So, my understanding is if this my bearing would have been 180 for 78 degrees 12 minutes, then it would have been North Pole.
No, beta. If the bearing of 7812 was also south, that means this full circle will be between Z and S.
Yeah, no, sir. And opposite to what the question is, like 18 degrees would have been 000, and this thing, then it would have been the North Pole.
Exactly, beta. If 1854 was north and 7812 was south, then it would be the north pole.
Okay, sir. Even the equinoctial would have. Okay, sir. Understood. So, so if they give us intermediate bearings, what about that, sir?
We will do those questions also.
Okay, sir.
Okay, beta. Great. One item is obtained. Let's get the second item. Let's move ahead now. We have the declination. The next thing which we need to find is the latitude of the observer. Now finding the latitude is easy. In this particular diagram, the latitude is represented by ZQ. Z is the zenith, Q is the equinoctial. So ZQ represents the latitude of the observer. And this is equal to PS or SP. SP or PS is the elevation of the pole or the altitude of the pole, and we are aware that the elevation of the pole is always equal to the latitude of the observer. So if we find out the value of PS, it will give us the latitude. Now PS is easy to find. PS is basically equal to SY plus PY. SY is given as 1854, that is the altitude of the star. So we know SY is 1854 and Py is nothing but the polar distance of the star, which we had already found out. So Sy 1854 and Py is the polar distance which we already found was 4127. So when you add these two, Sy plus Py gives you the elevation of the pole equal to the latitude of the observer, and it comes to 60 degrees 21 minute south. So both the required items have been obtained. The declination of the star is found and the latitude of the observer is also obtained. Any doubts, beta?
Clear.
Great, beta. Very good. Let's see one more question. Let's move on to the next question. To an observer, the true altitude of a star when on the meridian at upper and lower transits. So upper and lower transits tell us that this star is a circumpolar star. Only circumpolar body transits twice in a day. Transit means it passes the observer's meridian, or it comes north or south of the observer 2 times in a day. And upper and lower transit or upper and lower marpas occurs only if a body is circumpolar. So its altitude was 80 degree 9 minutes in the south bearing, southerly bearing, and 11 degree 45 minutes on the northerly bearing. Calculate its true altitude when on the prime vertical. So let's try to put all the required information in the diagram. We have the rational horizon. We mark the NESW points. We mark the center of the diagram as the zenith of the observer. Let's now put all the information given to us. Now you see the upper transit of the star was 80 degree 9 minutes south. Southerly bearing is represented by line ZS, and S point is the horizon. From the horizon 80 degrees 9 minutes away. So from S 80 degrees 9 minutes away is where 80 degrees 9 minutes away is where the star is. And the star is at northerly bearing with a altitude of 1145. Northerly bearing is represented by line ZN. So on this line Zn, from point N, which is the horizon, we come up 11 degree 45 minutes. This is where the star is. So the same star is observed at upper and lower transits in these two locations. Now the declination circle of the star should be passing from both these locations. It is the same star, and there is only one possibility of having a declination circle like that. The possibility is a circle in this particular way. So you see the declination circle of the star passing from both the positions of the star. We can draw the declination circle. Now we know at the center of the declination circle, all the declination circles are centered at the pole. So let's go to the center of this declination circle. This is where the center is, and this is where the pole is. Pole is at the center of all the declination circles. Any doubts up to here, beta? Good. Now, once we have the pole, we can also show the equinoctial in the diagram. The equinoctial will be 90 degrees away from the pole. This is where the Q point would be. And it always passes from east and west points. So WQE is the equinoctial. Now the direction in which the body will be moving is rising from east, going in this particular direction and setting in west. So this tells us the star will also be moving in this particular direction. That is what is shown by the two green arrows. This is the direction in which the star will be moving. Now they have asked us to calculate the true altitude of the star when it is on the prime vertical circle. Now what is this prime vertical circle? Prime vertical circle is the vertical circle passing from east and west points. So in this rational horizon diagram, the line WZE represents the prime vertical circle. The line NZS is called as the principal vertical circle. Not required in this question right now, but just for your information, NZS is the principal vertical circle. WZE is the prime vertical circle. So we now need to know the altitude of the star when it is on the prime vertical. So when the star is moving on its declination circle, it is going to cross the prime vertical at this particular location. So we have marked the same star when it is on the prime vertical. Let's name this as X. Now there is one more location where the star will be on the prime vertical, that is this particular location. If you want, you can pick up this location also. In both the cases, the working as well as the answer will be the same. So whichever location out of two you want can be picked up and the question worked out. So we have marked the star X here. We have the X, we have the zenith at Z, we have the pole at P. Now we can draw the PZX triangle. The missing side is the celestial meridian of this star. So let's mark the celestial meridian also. You have the celestial meridian marked as PX in maroon color. Now you can concentrate on the PZX triangle. PZX triangle. This is a spherical triangle and is a special spherical triangle because we have a right angle at Z. We have a right angle at point Z. Now what we need to know is the altitude of the star when it is on the prime vertical. So what we are going to do is, you see, we have S to this particular star, this arc known to us. We have N to this particular star arc known to us. Now I can easily find out the diameter of the declination circle of the star. The diameter will be 180 minus 1145 minus 8009. Exactly similar to what we did in the previous questions. So when we halve the diameter, we get the polar distance of the star, polar distance, which is Px. So Px, the polar distance, is known to us. Now once the polar distance is known, we have the polar distance. You can follow the laser pointer on the screen. Pole to this particular star is the radius of this circle, which is the polar distance. Once it is known, we can add polar distance and 1145. When we add the polar distance and 1145, we get the value of NP. And this NP is the elevation of the pole and equal to the latitude of the observer. Once NP is calculated, NP is obtained, we can also find PZ. PZ is the colat, 90 minus latitude or 90 minus NP. So you see in this triangle PZX, the polar distance of the star is known to us. The colat, which is PZ, is also known to us. It's a special spherical triangle. So you apply the Napier's rule and you find the side ZX. So ZX is nothing but the true zenith distance of the star. 90 minus ZX is going to give us the altitude EX. EX is the altitude of the star. It is 90 minus ZX and it comes out to be 60 degrees 20.4 minutes. Any doubts, beta? Understood?
Sir,
Go ahead.
sir, I'm just facing difficulty with the azimuth, or here also, sir, you are taken in PZ extra angle Z is 90 degree. Can you
Okay.
explain, sir, angle Z why it is 90? And
Okay,
other
beta.
things, sir, for placing body.
One by one.
Yes, sir.
पहले ये 90 निकालते हैं बेटा.
Okay,
Okay.
sir. Yes, sir. Yes, sir.
Okay. Now P is the pole, beta. Can you tell me what is the direction of ZPN line? ZPN. The direction will be 0, 0, 0. You agree?
0, 0. Yes, sir.
Okay. Now tell me the direction of ZXE line. E is the easterly direction. It has to be 090.
Yes, sir.
So if Zn is 000 and Ze is 090, the angle of cut between them has to be 90 degrees.
90. Yes, sir.
So Z becomes 90. Clear?
Okay. Yes, sir.
Now the next out, beta.
Next, sir, for positioning of any celestial body, Z will play the special role. Where is the body? Like in this case, body is on the 90 degree. सर सो जेड का कैलकुलेशन जो है ना सर वो कि आपका बॉडी कहाँ पे वो थोड़ा सा मुझे सर क्लियर नहीं हो रहा है जैसे आपका एजीमथ के बेस पे अपन कैलकुलेट करते हैं 20 डिग्री 30 डिग्री या पीजेड एक्स्ट्रा एंगल में कहाँ पे हो सकता है
ओके 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 बेटा
If you
ये वाला
explain,
सवाल
sir.
मैं समझ गया
ये वाला हो
तुम्हारी
गया, sir.
प्रॉब्लम ये वाला हो गया
एंड
ना
अगर उसके साथ LHA इंक्लूड हो गया देन थोड़ा सा और
देन इट विल बिकम रियली कॉम्प्लिकेटेड एंड ट्रिकी राइट
यस
सो
सर
कोई बात नहीं बेटा हम LHA भी इंक्लूड कर देंगे और एजीमुथ भी निकालेंगे वी विल डू दोस क्वेश्चंस जस्ट वेट
ओके सर
ओके ग्रेट वेरी गुड और कोई डाउट्स बेटा एनी मोर डाउट्स
नो सर थैंक यू
Sir,
ओके
here we have discussed the body rises from east to west, right? But
Right.
GHA and LHA all measured towards westerly, correct, sir? So can you please tell me, sir, why is the difference?
Okay beta okay see all the bodies rise in east and they set in the westerly direction or they travel from east to west.
Yes, sir.
Okay. Now your question is why is the GHA measured westerly? Okay.
Yes, sir.
Beta, if the body is going from east to west in the westerly direction and you are measuring the angle westerly, every hour the angle is going to increase, right?
Yes, sir.
Now, if you are measuring it easterly, every hour the angle would decrease. From 360, it will become 345 after 1 hour. Then it will become 330 after 2 hours. So the angle reducing every hour will be very odd and complicated. That's why we have chosen the westerly direction to measure the GHA, the SHA, the LHA.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Great, beta. Very good. So I'm closing down the presentation. We are done with circumpolar bodies. Very good. Excellent. So a very, very important concept understood. That is the circumpolar bodies. So let's take a short break, beta. 5 minutes की break लेते हैं.
Assignments for this one, sir?
It will come, but not now. Little later. It will come little later.
Okay.
Okay. So take a break. 5 minutes break. Get your batteries recharged, and then we move on to twilight. Okay.
Okay, sir.
Okay. Okay, beta, back, ready? आगे बेटा चलें ट्वाइलाइट. Okay, all right. Let's go. Let's now understand the concept of twilight. Now, twilight is the light received from the sun when the sun is below our horizon. Now, we receive the light from the sun when it is above our horizon, and we call that light as sunlight. But we also receive some light when the sun is below our horizon and close to it, and that is the light which we call as twilight. This happens before sunrise in the morning and after sunset in the evening. So as you can see in this diagram, the right side of the diagram represents the sunrise, and before sunrise for this particular period, the dark blue color sector which is marked here on the right side of the diagram represents the period when we get the twilight. And when the sun goes on the western horizon, you can see in the diagram, the sun going in the western horizon sets at this particular instant, and after setting we keep on receiving the light which is called as twilight when the sun is in this dark blue color sector. So in this particular sector we receive the twilight in the evening. Now, even though the sun is below our horizon, it still illuminates the upper layers of the atmosphere. Now, this happens because of the refraction and scattering principle. The light undergoes refraction in the atmosphere and it gets scattered in various directions, because of which we are able to see the light even after the sun has set or the sun has gone below our horizon. Now, in the evening, when the sun sets, till the time sun is there in the sky, we receive the sunlight. Now, after the sun has set, we do not have any sunlight. What we receive now is the twilight. The twilight is available to us till the time the sun goes 18 degrees below our horizon. So you can consider this 18 degrees as a negative altitude of the sun. Till the time the sun is within 18 degrees of our horizon, we keep on receiving this twilight, and after the sun crosses this 18 degrees belt, after that there is total darkness and we do not receive any light from the sun. So in the evening time, the twilight commences at sunset and it continues up to the point where the sun is 18 degrees below the horizon, and after that the night starts. So after 18 degrees, there is no light which we receive from the sun. It is totally dark. Now in the morning, the twilight commences when the sun is 18 degrees below our horizon. It reaches at a point when it is 18 degrees below our horizon. That is the period when the twilight starts. Right now, the laser pointer is showing that instant when the sun is 18 degrees below the horizon. We keep on receiving this twilight till sunrise, and as soon as the sun rises, the twilight ceases and we are able to see the sun and receive the sunlight. Now this entire period of 18 degrees is divided into 3 different stages, and we call these 3 different stages as civil twilight, nautical twilight, and astronomical twilight. Now let us see these 3 stages of twilight one by one. Now we have zoomed into the right side portion of the diagram depicting the sunrise. Now you see the sun is at this instant at a particular time. As the sun approaches towards our horizon, right now it is night, it is totally dark, we are not receiving any light from the sun. Now when the sun reaches at this particular point, you can follow the laser pointer on the screen. When the sun reaches at this particular point, now this point is 18 degrees below the horizon. You can see the angle also mentioned here. The sun has reached 18 degrees below the horizon. Now this is the instant when the astronomical twilight commences.
Sir, at this point, we are estimating sun's upper limb or lower limb, sir?
Beta, speaking theoretically, the center.
Okay, sir.
These are the center's altitudes below the horizon.
So that means the twilight stops when center comes at civil twilight, right?
No. The stopping period is when the upper limb of the sun comes above the horizon.
Okay, sir.
Okay, so there's a difference.
Okay, sir.
Okay. The astronomical twilight has commenced at this particular instant, and we are able to receive some light, though very, very little, at this particular point of time from the sun. After this instant, the sun keeps on coming closer to the horizon, and the altitude it was initially minus 18 degrees when the twilight started. Now it starts to come down, minus 17, minus 16, minus 15, and so on. Now at this particular instant, the sun is 12 degrees below the horizon. You can see this angle is 12 degrees now. It is marked in the diagram. Now this is the instant when the sun is 12 degrees below the horizon, and at this particular instant the nautical twilight commences. The nautical twilight has commenced here. After this instant, the sun keeps on coming closer to the horizon, and at this particular instant, you can follow the laser pointer. At this particular instant, the sun is 6 degrees below the horizon. The angle is shown in the diagram. And at this particular point, when the sun is 6 degrees below the horizon, civil twilight commences. Now, all these 3 twilights, they go up to the sunrise. Each of them, the astronomical twilight, nautical twilight, and civil twilight, lasts until the visible sunrise. Visible sunrise is when the sun's upper limb appears on our visible horizon. That's the instant we call as visible sunrise. So you see, the commencement time of all the 3 twilights are different. Astronomical twilight commences when the sun is 18 degrees below the horizon. Nautical twilight commences when the center of the sun is 12 degrees below the horizon. Civil twilight commences when the sun is 6 degrees below the horizon. And all 3 of them, they last until the visible sunrise, when the upper limb of the sun appears on our visible horizon. Now, out of this entire period, as far as navigators are concerned, as far as site taking is concerned, which is the most suitable period for us? The most suitable period for us is between 12 degrees and 6 degrees. This particular period, which is represented in blue, the upper period is represented in light blue, and the bottommost period is represented in dark blue. The middle portion is what is important from the point of view of the navigator for the purpose of site taking. Now, this period is basically the commencement of nautical twilight to the commencement of civil twilight. The suitable period for us for site taking starts at the commencement of nautical twilight in the morning, and it remains up to the commencement of the civil twilight in the morning. Now, why is this period suitable to us? If you go beyond this particular period into the dark blue zone, now in the dark blue zone, the sun is 18 degrees to 12 degrees below the horizon. With the sun more than 12 degrees below the horizon, there is very less light for the horizon to be clear to us. The horizon may not be very much clear to us because the light which we are receiving is very, very, very low. Now, as the sun reaches about 12 degrees below the horizon, we have sufficient light with which the horizon can be clearly seen. And we know for the purpose of site taking, we need to have the horizon as well as the body in our sight. So we can start our site taking at this instant when the sun is 12 degrees below the horizon. And this suitable period continues up to the sun going 6 degrees below the horizon. Now, when the sun reaches 6 degrees below the horizon, you see as it is coming closer to the horizon from 18 to 12 and from 12 to 6 now, more and more light is visible to us on the eastern horizon. Now, at this particular instant, when it is just 6 degrees below our horizon, there is so much of light on the eastern horizon that stars and other celestial bodies, stars as well as the planet, they start to disappear. So after 6 degrees, we may not be able to easily identify, find out the stars for the purpose of site taking. It is so bright in the sky that the stars start to disappear. So this period is also not very suitable for us for the purpose of site taking. The most suitable period is commencement of nautical twilight when the sun is 12 degrees below the horizon to commencement of civil twilight when the sun is 6 degrees below the horizon. Any doubts, beta?
Sir, astronomical twilight maybe it will be clear, sir. We can see the stars and planets. And
Beta, we cannot see the horizon. In astronomical twilight, from 18 degrees to 12 degrees, we cannot see the horizon because the light is too less.
We cannot use the sextant to bring the object to the horizon, right, sir?
Exactly, that's right. Stars are very bright. Stars, planet, everything is very bright. But to take the altitude, you need to look the horizon also. So horizon is what is not visible.
Okay.
Right, sir. Right. Thank you.
Okay, okay. Now we have zoomed into the sunset part of the diagram. This is the instant when the sunset takes place. So in the evening, as soon as the sun sets, as soon as we have a visible sunset, which means the sun's upper limb has disappeared from our visible horizon, this is the instant when all the three twilights commence. So the commencement time in the evening for all the three twilights is the visible sunset. The civil twilight continues till the time the sun is 6 degrees below the horizon. At this particular instant, the sun has gone 6 degrees below the horizon. You can see it is represented in the diagram also. Sun is 6 degrees below the horizon, and this is the period when civil twilight ends. The other two continue. The sun goes further down, and when the sun reaches at this particular instant, when it is 12 degrees below the horizon, so sun is at 12 degrees below the horizon here, the nautical twilight ends. Astronomical twilight still continues. The sun also moves down, and when the sun reaches at this particular instant, when it is 18 degrees below the horizon, the astronomical twilight ends. So we can clearly see that all the three twilights begin at the time of visible sunset. Civil twilight continues till the sun is 6 degrees below the horizon. Nautical twilight continues till the time sun is 12 degrees below the horizon, and astronomical twilight continues till the time the sun is 18 degrees below the horizon. After 18 degrees, there is no light received from the sun, and we have total darkness or the night. Now, in this case also, the suitable period for us for the purpose of sight taking is between 6 degrees and 12 degrees, which in this case is the ending of the civil twilight to the ending of the nautical twilight. This is the most suitable period for us. Before this period, the sun is within 0 to 6 degrees of the horizon, and there is too much light for the stars and planet to be visible to us. There is so much light that stars and planet may not be visible. Between 6 to 12 degrees, the light has decreased now. The stars and planets start to appear in the sky. They gain sufficient brightness so that we can observe them by the sextant for the purpose of sight taking. And after this interval, that means when the sun has gone below the horizon more than 12 degrees, there is so less light available from the sun that the horizon is not clear to us. The stars and planets are shining very bright, but the horizon being not visible, it will not be possible to take the sight. So again, the light blue portion is not suitable because there is too much light. The dark blue portion is not suitable because there is too less light for the horizon to be visible. The suitable period for us is the middle period, the blue color period, which is represented by minus 6 degrees to minus 12 degrees altitude of the sun. This is the most suitable period in the case of evening twilight. Now, be careful and be clear in your mind that in the morning, the suitable period was commencement of nautical to commencement of civil, whereas in the evening, the suitable period is ending of civil to ending of nautical. Now, practically, if you are trying to take a star sight, you need to be standby on the bridge wing ready with a sextant at this particular instant. That is when the sun is 6 degrees below the horizon. This is the instant when we are ready with the sextant on the bridge wing for the purpose of taking the sight, because this is the beginning of the suitable period for us. If we are ready here, we can observe the horizon also, we can observe the celestial body also, and a sight can be taken. If you are standby at this particular instant, that is ending of the nautical twilight, it will not be of use because the horizon is going to disappear now. So we need to be standby. This is the critical time as far as the evening twilight is concerned. That is the ending of civil twilight. Now in the case of morning, the beginning of the suitable period is when the nautical twilight commences. Because in the morning, when the sun is coming from below the horizon, it reaches 12 degrees below the horizon. That is where the nautical twilight commences. At that time, the stars are visible in the sky, the horizon also starts to appear, and a sight is possible. So the beginning of the suitable period in the morning is commencement of the nautical twilight, and the beginning of the suitable period in the evening is the ending of the civil twilight. Any doubts, beta? Very good. Now we have understood the concept of twilight. One issue which we face when we solve the numerical question involving the concept of twilight is how to show this altitude of 0 to minus 18, that is negative altitude, in our rational horizon diagram. So let us try to see this. We have the rational horizon diagram on the screen now. We have the NSEW point, we have the zenith in the center. Now we are aware that this rational horizon diagram represents the zone from the zenith, which is at 90 degree altitude, to our rational horizon, which represents 0 degree altitude. So all the points which are within this rational horizon circle represent the altitude from 0 degrees to 90 degrees. Now when we want to show the twilight zone in this diagram, we need to show a altitude of minus 18 up to minus 18. Let's assume a observer in latitude of 15 degrees north. So we can see the latitude coming up on the screen. ZQ represents the latitude. Let's now draw the equinoctial for this particular observer. Equinoctial always passes from the east-west points and the Q point. Now we can also show the pole here. The pole is at this location, represented by P. Now when we want to show the twilight zone, which depicts 0 to minus 18 degree altitude, we are aware the zenith represents the zenith represents 90 degree altitude, and any point on the rational horizon represents 0 degree altitude. So if we want to go into a negative zone, we have to go outside the rational horizon. So this twilight zone has to be shown outside the rational horizon, which you can see in the diagram as the dotted line. So you can now easily visualize that zenith represents 90 degree altitude. As you go towards the horizon, the altitude decreases 80, 70, 60, 50, 40, 30, 20, 10. At the rational horizon, it is 0 degrees. And when you go beyond the rational horizon, the altitude goes in the negative zone. The width of this particular band, which we have made, is 18 degrees, because the twilight zone remains till the time the sun has gone 18 degrees below the horizon. Now let's try to show the sun also in this particular diagram. Let's assume that the declination of the sun on this particular day was 12 degrees north. So sun is 12 degrees north of the equinoctial. You can see the sun coming up in the diagram. We can now also draw the declination circle of the sun. All the declination circles are parallel to the equinoctial and are centered at the pole. So we can see the declination circle coming up. Now when the sun follows this declination circle, the sun is going to enter the twilight zone at this particular point. You can see the laser pointer on the screen. At this particular point, the sun is going to enter the twilight zone. So this is the commencement of the astronomical twilight in the morning. The twilight continues when the sun is within this particular 18 degree zone. And at this particular point, where the laser pointer is right now, you have the sunrise. So this thick maroon line represents the twilight period for the sun. Then we have the sunrise. The sun moves in the sky. At this particular point, the sun crosses our meridian. We have the Marpas. Then the sun goes west of the meridian. At this particular point, the sun goes below our rational horizon. So this is the point where the evening twilight starts. The twilight continues till the time the sun is within this 18 degrees belt. And at this particular point, when the sun leaves the 18 degree belt, the astronomical twilight ends. So you can represent these points. At point A is the commencement of the morning twilight. At point B is the ending of the morning twilight or the sunrise. Then in the evening time at point C, we have the sunset and the commencement of the evening twilight. And at point delta, the evening twilight ends and the sun goes beyond the 18 degrees belt. So this is how this negative altitude of 18 degrees can be shown in the rational horizon diagram, and it helps us to solve any numerical problems related to twilight. Now this diagram shows 18 degrees belt, which represents astronomical twilight. In a particular question, if they ask you about nautical twilight, then this belt is going to reduce to 12 degrees. And in case civil twilight question is asked to us, this belt is going to be reduced to 6 degrees width. Any doubts, beta?
Sir,
Go ahead.
sir, for calculation of during sunset, civil twilight duration commencement is start from sunset time, sir, and means that is just opposite to during sunrise and sunset, sir, or commencement of civil twilights.
Okay, beta. Let me show you the diagram. You are talking about the sunset, na? Sunset?
Yes, sir. Sunset.
Okay. See here, beta. All the three twilights, they commence at sunset.
So, like a civil twilights period, when we are going to solve the question like any particular question, so civil twilight period commencement timing will take which one, sir? Sunset time from that period is taking for calculation.
Okay. Now you have to first see whether it is AM or PM. It will be given in the question. If it is PM and you want the time for commencement of civil twilight, it will be sunset. Even the commencement of nautical twilight will be sunset. Even the commencement of astronomical twilight will be sunset.
No, sir, I'm asking particular question if something they are asking like a given for civil twilight. So civil column also given some values, but commencement for calculation which we are going to take that sunset time is using for calculation or we will use for civil twilight time, sir.
Okay, beta. Beta, you have the almanac. Almanac है
Yes,
आपके
sir, I
पास?
have almanac, sir.
Just open up any day page, beta. Any daily page, open up the almanac.
Yes, sir.
Now in the evening time, have a look. The first time which is given is the sunset time.
Sunset time, correct, sir.
Okay. After that, the time which is given is civil.
Civil, yeah.
They have just mentioned civil. That is
Yes,
the
sir.
ending of the civil twilight, right?
Okay, okay, sir.
And after that, the time given is the nautical. That is the ending of the nautical twilight.
End time is given. So commencement will be
Right.
just before one column.
Commencement
So
will be sunrise. Sorry, sunset. Commencement will be sunset.
sir. Okay, sir.
Okay. And in the
Okay, sir.
morning, now you go in the top part of the table. In the morning, the first time which is given is nautical.
Nautical.
Then the next
So this
time which is given is
commencement
civil.
time.
Yes, that's
Okay.
right.
Okay, okay, sir. Okay, sir.
Clear? Clear now?
Beginning time. Only the beginning time, right?
Yes. Morning times are given in the almanac are the beginning times because the ending is at sunrise. Evening times given in the almanac under twilights are the ending times because the commencement is the sunset.
Okay, sir.
Okay, sir. Thank you, sir.
Okay. Great, beta. So let me now show you one more concept. This is condition for twilight throughout the night. Now, one more concept which is sometime asked in the questions is what are the conditions for twilight throughout the night? So let me explain you with the help of this diagram, what do they mean by the term twilight throughout the night? So we have taken a particular observer. we have shown the rational horizon for this particular observer, and we have shown the 18 degrees twilight zone also, going into a altitude of up to minus 18. Now let's assume that the declination of the sun on a particular day is this much, from point Q up to the sun. This is the declination of the sun. Now if the declination is this much, the sun is going to move on a declination circle. All the declination circles are centered at the pole, so we have the pole here. Now the sun at this particular point will be passing the meridian. After Marpas, the sun moves, and at point A we are going to have the sunset. Now as the sun sets, the twilight is going to commence, so we have the commencement of the evening twilight. Now you can see clearly here that the motion of the sun when it goes below our horizon from point A up to here and then going up to point Bravo. You can follow the laser pointer. From point A, the sun travels up to here at this particular point and then goes up to point B. Now when the sun reaches at point B, point Bravo, it is going to be the sunrise again, and the sun is going to come above our horizon. Now the duration of the night for this particular observer is from point A going up to point B. Alpha to Bravo represents the night for this particular observer. If you observe carefully, throughout this interval, that means from the sunset at point Alpha up to the next day sunrise at point Bravo, the sun has remained within the 18 degrees belt. It has not gone below the 18 degrees belt at any time. So this tells us that throughout the night, that means from point Alpha to point Bravo, the twilight continues. The twilight does not end in between. If the declination of the sun was lower, was lesser, then as we saw in the previous slide, the sun would be leaving this 18 degree zone at some point of time, ending the twilight. But in this particular case, during the night time from Alpha to Bravo, the sun never leaves the twilight band of 18 degrees, thus making a condition in which the twilight continues throughout the night. Now you should remember the conditions which make this phenomena possible. For twilight to continue throughout the night, one thing which you can notice here is the latitude and declination should always be of the same names. This is the first condition to be met. The latitude and declination should be of the same names. The second condition which we need to meet is latitude plus declination should be less than 90 so that the sun will set. If the latitude plus declination becomes greater than 90, then you see the sun is going to fulfill the circumpolar criteria. If the sun becomes circumpolar, there will be no night. If there is no night, there is no chance of any twilight occurring. So that's why latitude plus declination should be less than 90 so that the sun is not circumpolar and the sun sets and we have night for some part of 24 hours.
Sir, can you
The
explain
third
this second
condition
point
which
in
should
the
be met
diagram,
is
sir?
latitude plus declination plus 18 should be greater than or equal to 90 degrees. Latitude plus declination plus 18 should be greater than or equal to 90 degrees. This third condition certifies that the sun doesn't go below the twilight belt. So when this third condition is fulfilled, that is latitude plus declination plus 18 greater than equal to 90, this ensures that the sun will not go beyond the 18 degrees belt or below the 18 degrees belt, and the twilight will not end at any time after sunset till the next day sunrise. So these are the three conditions which should be fulfilled. Lat and dec same name, latitude plus declination less than 90, latitude plus declination plus 18 greater than equal to 90 for twilight to remain throughout the night.
Sir, can you show the second condition on the diagram, sir? I cannot visualize.
Okay, beta. Okay. Beta, you remember the circumpolar criteria?
Yes, sir. It should be of same name and latitude and declination greater than 90 degree.
Very good. So no need to visualize, beta. If lat plus dec becomes greater than equal to 90, the sun would become circumpolar. If it is circumpolar, there will be no night and there will be no twilight. As simple as that.
Yes, sir.
Right? So you can have a logical explanation in that way. No need to show it in the diagram.
Okay, sir. Okay.
You can show it here, but that will unnecessarily make it complicated.
Okay.
Okay. Any more doubts, beta? Okay. Great. Very good, beta. So that completes our twilight topic also. Sometime you get a straight question on this. What are the conditions for twilight throughout the night? So this is the answer. These three conditions you have to write down. Okay, great. So I'm closing the presentation now. Okay, beta. All right. So we have covered circumpolar as well as the twilight topics. And with this knowledge, beta, with this circumpolar bodies and the twilight knowledge, we are now ready to go into our next important topic, that is stars suitable for sight. So that's the topic which tomorrow. It's a lengthy topic, okay, and it's a tricky, complicated topic. And we will be using these two concepts, the concepts of twilight as well as the concepts of circumpolar bodies in that. Right, beta? So that we will be picking tomorrow. And yeah. So lengthy topic. Let's see if we can close it out tomorrow. Otherwise, one more class for that.
Sir, can you share this assignment for the PZX triangle?
I'm not sharing it now, beta, because I have to cover few more questions with you on PZX before I share that assignment. Some more concepts need to be cleared. So the concepts of LHA, concepts of motion of the bodies. So I will share that afterwards.
So
Okay.
this question 5 and 6, that assignment which we had for this 14 questions, that is enough, sir, to
Okay,
go for exam?
beta, that will clarify all your basics. After
Okay.
you are confident and you have completed the assignment, go into past papers and try solving those questions. See for yourself.
Okay.
Sir, one
Sir,
more question about side solving methods. This is only a basic question. So, suppose in question paper they have mentioned that we have to find a PL, and they have not mentioned that we have to find out observe long or maybe the intercept. So, can we solve this question from both from any long background intercept?
Beta, I had shared a PDF document with you. How to determine the method to solve if not given in the question. Did you go through that?
I think I missed it, sir.
Okay, just
Because
see it there.
I solved all the questions, sir. So we don't have any problem with this side solving methods. But this just a doubt came in my mind that if observe long or intercept is not given and they told us to find the PL. So can we go through any method?
No, just go through that. Other people, beta, did you go through that document which I had sent you?
yes, sir.
Yes, sir.
So
But in
please
that,
go through that.
in the document, it is not given that any difference of for long background and intercept. You can solve it any time.
Beta, see, whatever cues are given in the question, I have mentioned in that. Okay. So if you get any of the cues which are given in that PDF document, you know this is the method to be used. If nothing is given, then it is entirely up to you, beta. You can just write there, since the method is not specified in the question, we are picking up long bicron or we are picking up intercept and solving it by that. You can do that if no indication is given to you at all.
Okay, sir. Thank you.
Okay.
Okay. How a indication can be given, that I have mentioned. मैंने वहाँ पे 5 steps mention किए हैं. So just go through that document, it will clarify. If none of them is applicable, then your choice.
Okay, sir. Thank you, sir.
Sir, my question is regarding PZX triangle to highlight for azimuth and sir LHA part, sir. जैसे डिसाइड
Okay.
करते हैं ना पोजीशन को, सो वो थोड़ा सा एक बार और अच्छे से एक्सप्लेन जरूरत है.
No problem. Just wait for a couple of classes. Tomorrow we are doing star suitable for sight. After that, I will pick up these type of questions which you are saying.
सर एक्चुअली जेड का जो कैलकुलेशन आपने आज किया था ना, जो सरकमपोलर बॉडी में आपने 180 ले लिया था, अगर 180 ना हो के कुछ और हुआ जैसे समथिंग,
और कुछ हो नहीं सकता बेटा.
नहीं, वो तो सरकमपोलर केस में है ना सर, दैट इज ओनली ऑब्जर्वर मेरिडियन.
180 तो नॉर्थ टू साउथ था. नॉर्थ टू साउथ तो 180 रहेगा, वेदर बॉडी इज सर्कमपोलर और नॉट.
उस सरकमपोलर के केस में नहीं बात कर रहा हूँ सर, मैं डिफरेंट बात कर रहा हूँ, जब अजीमत कुछ और आता था सर.
So you are talking of the PZX questions which are non-circumpolar, right?
Yes sir, not circumpolar sir.
We will do them in a class after tomorrow.
Okay sir.
Okay?
Okay sir.
Sir,
Okay.
likewise, we have assignment and also solved questions like that. We have any for chart work, sir, like assignment questions with solutions?
Beta, Vishnu sir has given you, na?
Sir, he has given only the assignment questions only, but the solving to refer in case of any doubt, like I'm asking.
Answers are also there, na? So match your answers. Match the working.
Okay, sir.
So I have for Selnab.
Okay, sir.
Okay. Okay.
Sir,
beta, great. Go
sir,
ahead.
the circumpolar body is second solved. Can you just tell me one more, sir, this last part, this ZX, how did you get this? I mean,
ZX.
I mean, you told me that I calculated true attitude and on primatical. That last part, can you just tell me once, sir, if you don't mind?
You mean to say, how did we calculate ZX?
Yes, sir. In PZX triangle, in that particular question, in PZX triangle, I got the value of PZ and PX. And you solve this ZX using this numerical trigonometry, I mean, composite problem.
Okay, listen to me, beta. Listen to me. I understood your problem. In that triangle, we have PZ known to us. We have the PX also known to us. Two parts of the triangle or two sides of the triangles are known, right? Right?
Yes, sir.
Now that triangle is a special spherical triangle because angle Z is 90. Right?
Yes, yes.
In a special spherical triangle, we can apply the Napier's rule. Napier rule says that if you know any two parts of the triangle, you can calculate any other part using the two Napier formula, beta.
Understood, sir. Sir, we can't do like this, sir.